This is a report from the Heavy Flavor Task Force on open heavy flavor. The purpose of the Heavy Flavor Task Force was to scrutinize the modeling components between different models and to quantify how the uncertainties of the modelings impact the extraction of the heavy quark transport coefficient. And to that end, 2 on-site meetings were already convened at GSI in July and December of 2016. So that's already 4.5 years ago. During these 2 meetings, key questions or problems were addressed, including comparisons of conceptual opinions between different models, and comparisons of bulk medium evolution models and their impact, comparison and the impact of heavy quark hydronization, in particular coalescence, which actually represents in my opinion, the biggest uncertainty from a theoretical point of view. And also the comparison of transport coefficients, including their temperature and momentum dependence. And finally, the comparison between full Boltzmann simulation and the Lantern simulation of heavy quark diffusion in quark plasma. And the summary made from these 2 meetings was already published in 2018. So in my talk, I will go through the comparisons of all these components as shown here between different models and discuss the conceptual opinions of each model when appropriate. First, initial charm quark spectra. This will be serving as kind of baseline for the simulation of heavy quark transport in quark plasma. So in most models, the initial charm quark spectrum was obtained from the generation of phono software. But some of models took the initial charm quark spectrum from like the PQCD model calculations. So we see at low PT this initial charm quark spectrum. It's still subject to significant uncertainties or variations between different models. The phono spectrum, the phono software was already able to get the dimensional spectrum in PP collisions very well after fragmentation. But in the phono software, there are 3 sets of parameters. So they represent another source of uncertainties in the initial charm quark spectrum. The impact of these parameters on charm quark IA as observable is shown here. So we see among 3 sets of parameters, the IA is subject to some uncertainty at low PT below 2 GeV. But after hydronization, I mean, at level of D metal, the uncertainties seem much less. So it is important to adopt a common PP baseline. And then we know at LC energies, charm is subject to shadowing because of the shadowing of Hydronic diffusion functions as a small x. Then as a small momentum, small transverse momentum, there will be some depletion of the charm quark cross section at low PT. Taking the central value of the EPS 09 parameterization of the Hydronic diffusion function, one would get like a 20% reduction of the total charm cross section. I mean after integration of the PT spectrum. Then the input charm quark spectrum at the starting point of simulating the charm quark diffusion in quark plasma should be obtained by convoluting phonon PP charm quark spectrum with the RAA of charm quark that arises solely from the shadowing effect, from the coding inverse effect. This was already shown in a database constructed by this task force. And then the charm quark shadowing, different shadowing would have different impact on the charm quark RA, of course, especially at low PT. And also after hydrogenization, also at level of dimensional RA. So this represents a significant uncertainty. If you take different charm shadowing parameterizations, then get a different RA, especially if the shadowing is pretty large, it's then the largest shadowing, then the RA of the dimension will be all below 1, below unity, in all PT range, in all PT range. Okay, then the bulk evolution models. The flow velocity, the distribution and evolution of the flow velocities, and also the temperatures from the bulk evolution model, namely from hydro, provide a link between the heavy quark hydrogenization and their spectral evolution. So different hydro models were used between different models. In URQMD, time length in these models, ideal hydro was used, and in some other models, viscous hydro was used. But in all these bulk evolution models, the lattice equation of states was used for the quark plasma phase. And then the initialization time of the hydro would be ranging from 0.3 to 0.6. This may be a small uncertainty, finally. The hydrogenization temperature, I mean the end of QGP phase, at which you stop the diffusion of quark plasma and start to do hydrogenization, was taken as mostly as 160 to 170 MeV. But in different hydro models, different bulk evolution models, there seems to be a significant discrepancy for the entropy you put in. This is reflected in the yield of the pions and the protons also. For example, in 0 to 10% lead fissions at 2.76 TeV, the experimental results of the pion yield for unit rapidity is around like 670. And you see there's a significant variation between different models around this experimental value. And for proton also. So this got to be resolved. And then let's look at the flow as imprinted from different hydro bulk evolution model at DC. So this is really just a snapshot at DC. So this is the direct pion spectrum and proton spectrum. We see for direct pion, between different models, there's a agreement within only like 20% in magnitude, and also the peak structure of the pion spectrum, ENDPT. For protons, because it's more massive and it's more sensitive to radial flow, this variation is even larger. And the V2, for V2, there's a reasonable agreement between different models up to like 2 GeV. You can say that in mid-central conditions. Also for proton. So as I said, this is only a snapshot of the bulk evolution model at TC at that point. But I think, in my opinion, maybe we can plot the average radial flow the evolution, time evolution of the average radial flow, and also the time evolution of the energy momentum tensor anisotropy as a function of time. So this may provide a better measure of how the evolution model is working. And using different bulk evolution models would have also different impacts on the observables. To check this, charm quark simulation with common 5 times PQCD transport coefficients was performed between different models, or using the counterpart of cross section if one uses a Boltzmann full Boltzmann simulation. So with these parameters, the translated diffusion charm quark diffusion coefficients was 6, around 300 TeV. Then we can see, as shown here, for the charm quark RA, there is a reasonable 10% to 50% spread among the different medium evolutions. Except for this LBL CCNU model, which has a much smaller RA and a larger V2 also, because it was using massless thermal partons. That means the density of partons is significantly higher when multiplied by the cross section. So effectively, you have a larger thermalization rate or smaller spatial diffusion coefficient. And the Catania group also did a calculation with 5 times PQCD transport coefficients for the purpose of comparing different hydrogenation temperature, 155 and 170 MeV. We see the charm quark IA is insensitive to the variation of this hydrogenation temperature, but the V2 is, of course, it's significantly enhanced. It's getting to a lower hydrogenation temperature. This is not surprising because we know suppression as reflected in the RA is most effective in early stage of the evolution with high density. But the transfer of the V2 of the bulk, so charm quark is most effective around TC when the bulk V2 is already large. And so then I'm going to the hydrogenation part. Hydrogenation includes 2 parts: coalescence and fermentation. So in most models, instantaneous coalescence model plus fermentation were used. But in TAM model, the so-called resonance recognition model plus recognition was used. And in the power lag model, they used the immediate fermentation function. So that's was kind of similar to coalescence. And in most models, the light quark mass of 0.3 to 0.37 GeV as constant quark mass was used, except in Nansen model, a much smaller quark mass, light quark mass was used. This will be reflected in the RA and also V2. So now we look at the dimensional RA and V2. For RA, we see a flow bump emerges as a result of the coalescence. In most models, in most coalescence models, which is most pronounced with Nansen, as shown by this curve. Maybe this is due to the use of a smaller light quark mass, because that represents a larger light quark density. The V2 as a result of coalescence will be increased by 30 to 40% relative to the charm quark V2. And as high PT, it tends to just the charm quark V2. Hydrogenation effects may be more directly exhibited via the so-called HAA. So this is defined as the charm quark spectrum right before the hydrogenation, and the charm quark spectrum right dimensional spectrum right after the hydrogenization divided by the charm quark spectrum right before the hydrogenization. But in the dimensional spectrum, you have two components, remember, coalescence plus fragmentation. So now we see the HAA. See at high PT, the dimensional V2 is just the result of the shift of the charm quark spectrum. So at high PT, there are two layers of the leveling off between different models. I mean, the LBL CCNU model and the URQMD model, they have a significantly smaller HAA, but all other models are lined up. At low PT, the light quark PT is added to the charm quark through coalescence. So again, you see a flow bump. This is more pronounced in central collisions. And this is again most marked in the Nance model, also for V2. Finally, we did a model average. We did a model average for the dimensional RA and the V2. When using the common 5 times PQCD transport coefficient. But in this model average, the LBL, CCNU, and the PHFD results were taken out. So we see at high PT, this averaged RA quite overestimates the data by a factor of 2. And the V2 at low PT, the dimensional V2 is supposed to be a kind of gauge of the interaction of the coupling strengths of the charm quark with the medium through a diffusion or hydrogenization. But the data is also underestimated by the model average by a factor of 2. So the conclusion we can make here is the coupling strength with 5 times PQCD it's insufficient. And the spatial diffusion ds times 2 pi t must be significantly smaller than 6 for temperature below 300 MeV. Here we also did some comparison between the most used instantaneous coalescence model and the resonance recombination model. So the instantaneous coalescence model performed an instantaneous projection from quark to hadron in 3 momentum space. And the resonance recombination model it's a long time limit of the Boltzmann equation through resonance scatterings, which conserves energy and also guarantees equilibrium limits. Here we use the same charm quark spectrum input as TC obtained from the using the 5 times PQCD transport coefficient. Then we see for different light quark masses, 0 MeV, 300 to 500 MeV. In all these cases, we see the dimensional PT spectrum from resonance recombination model. It's softer than the instantaneous coalescence model result. This is understandable because we say the resonance recombination is always approaching the thermal limit. And the dimensional V2 obtained from resonance recombination model is a bit smaller than the instantaneous coalescence model results. This is also understood from the fact that the resonance recombination model allows for isotropic cross-section smearing. But the instantaneous coalescence model, the charm quark and light quark tend to be moving in a collinear way. Then transport coefficients. Here, the thermalization rates as a function of both momentum and temperature. So in In many models, the transport coefficient was calculated through a modified PQCD version. For example, in the Nance model, it uses running coupling RFS and reduced screening mass. But in Catania model, it uses the RFS, also running RFS, that is getting large around TC. And in the TAM model, the transport coefficient was calculated non-perturbatively using the T matrix that resounds the medium Coulomb plus confining force. So we see here we plot the charm quark thermalization rates at function of temperature, at function of momentum in different temperatures, 180 MeV, 300 MeV, 500 MeV. So at low PT, there's always a enhancement. At low momentum, there's always enhancements, especially in this is more pronounced in the T-matrix approach, which resounds the remnant confining force. And the temperature dependence of the thermalization rates is determined by the particle density versus reduced coupling. And for T-matrix approach, there is a little change for the thermalization rates between 200 and 500 MeV. But for PQCD calculation, if we fix the RFS, then it should be scaled with T squared. So here we compare the charm quark RA and V2 in a common hydro medium evolution model, but with different transport coefficients from PQCD, from the Nance model, and from the TAM model. So RA is high PT. As high PT, the TAM model shows a less suppression due to a smaller thermalization rates than 5 times PQCD. And V2 as low PT, the TAM model is V2 is larger than the 5 times PQCD. And the Nance transport coefficient results in a stronger suppression and a larger V2. And there are some other evaluations of transport coefficients. The PQCD, using PQCD approach, Gaimore calculated the momentum diffusion transport coefficients to next to leading order, but it suffers from poor convergence. And also lattice QCD calculations. This has been talked about a lot. And this is also another lattice results showing the charm correlations above TC, but not very far from TC. There seem to be significant charm light correlations, which could be like resonances. So above TC, not only charm degrees, but also composite degrees. So here we compare the Boltzmann full Boltzmann simulation and the Lantois simulation for charm quark diffusion with the common 5 PQCD transport coefficients. So this the charm quark RA and V2. See if the mesh is for charm quark mesh like 1.5 GeV, the Boltzmann, the RA charm quark RA from Boltzmann simulation is significantly larger than the Lantois simulation results. But the V2 is smaller than the Lantois results. This can be understood because the Lantois simulation relies on the so-called the Gaussian distribution of energy loss, but this is becoming less accurate toward high momentum. But when the quark mass becomes larger, for example, the bottom quark mass 4.5 GeV, then the difference between two simulation tools becomes very small. the summary. So in the task force, the modeling components for heavy quark probes were scrutinized and compared between different models. And the transport coefficients. One major conclusion was the transport coefficients must be significantly smaller than 5 times QCD. And the heavy quark has the potential of unraveling the microscopic dynamics of QCD matter, but one has to constrain the computation of transport coefficients using lattice observables, for example, the susceptibilities and spectral functions. And hadronization may be representing a major uncertainty and a discrepancy between different models. So this will be the primary area for further improvement. Perspectives and observables were also suggested from the two task force meetings. For example, the bottom observables and dimensions of its big structures, and also the hadronization of charm strange metals and charm baryons. And also high level jet in jets pair correlations. That is supposed to be a good tool to delineate the elastic and radiative energy loss. So, but over the past few years, significant progress has already been made on many aspects of these issues. These will be discussed in this online workshop. So thank you.
Thank you very much, Min, for this update on the Rapid Reaction Task Force. We still have very little time for a question or two, so Xinyan.
Okay, this is a very quick question. When you compare all the bulk evolution, and you only shoot the hadron spectrum at just freeze-out temperature, are those models all can describe the final hadron spectrum, especially like PT and V2 or V3?
This I don't know. It's not shown here, not shown in the summary publication. I think they are supposed to describe the bulk
because the spectrum
as kinetic result.
They vary a lot. They vary by a factor of 2, not 20%. If you look at low momentum case.
Yes.
Okay, so I think looking at the clock, we should continue. So thank you very much again, Min. And then we come to Jörg Eichelin, who will report on the heavy quark jet working group.
Yes, but I cannot share yet.
Min, you have to stop sharing, or I can probably also do this. Ah, perfect.
Is this visible?
Yes, we can see your slides.
Oh,
so,
perfect. So good morning, good afternoon, or good evening to everybody. And thank you very much for the organizer who charged me to talk about 2 meetings and which resulted in 2 papers, which are just listed here, where we try to make a comparison of different approaches to the heavy quark physics in the quark-gluon plasma. And I will concentrate today not so much on the hadronic sector, but more on the passage of these heavy quarks in the plasma. So I would like to come to the point, what have we learned so far by comparing the different models? This means that I first introduce what are the differences, then how we can compare it, all the different approaches, which are based on quite different transport theories and quite different calculations of the elementary cross-section. And then I would like to ask the question, how can we gain further insight by comparing and what can be concluded already nowadays. Now, at the end of the day, we would like to understand the passage of the heavy quarks in the plasma, but I think we are not so far yet. Now I have the problems that I can advance here. No, okay. So from the first glance that we heard already, the heavy quarks are an ideal probe for tomography of the quark-gluon plasma. They are initially created in hard processes and accessible, therefore, for PQCD calculations. We know from comparison of the spectra that high PT heavy quarks traverse the quark-gluon plasma without coming to an equilibrium with the plasma. And this means the information the heavy quarks carry is of a part of the memory of the trajectory. And so therefore we can ask them what actually they have suffered in the way through the plasma. They are sensitive to the properties of the plasma during expansion and not only sensitive to the final state like the mesons, which obey more or less, but very good extent, statistical laws and therefore come from equilibrium at the end of the expansion. Furthermore, the heavy quarks keep their identity while traversing the quark-gluon plasma, that in contradistinction to jets, which can convert a quark into a gluon, for example, but heavy quarks basically do not do this. They just pass the plasma without being converted in other particles. They are interacting strongly with the quark-gluon plasma in contradistinction to photons, so they can be a better messenger for the interaction with the plasma constituents. And the heavy quarks are basically not heavy, and therefore the changes of the masses, also we saw from Peter that it's a little bit, they do not change too much in the medium. And so therefore we have at least one scale which is not that dependent on the temperature of the plasma. But as usual, the devil is in the details. So when we would like to study these heavy quarks, and to make prediction what we can observe, then we have to know a lot of information about the situation in the heavy ion collisions. We have to know the distribution in momentum space and position of the hard collisions, which produce, first of all, the heavy quarks. So that can be done by FNLL and Glauber. The initial px distribution, momentum space and space distribution of the quark-gluon plasma particles. So there we need then the initial condition of the usual transport series, EPOS or PHST, or depending on the different, or the initial condition depending on Trento and the plasma. We need the formation time of heavy quarks and the quark-gluon plasma, because only after they are formed they can interact. And especially we have to address the question when the interaction starts. We have looked for the expansion of the plasma, whether it's a hydrodynamics or viscous hydrodynamics or transport series like in PHSC. We have to address the elementary interaction between heavy quarks and the quark-gluon plasma, what kind of interaction takes place. Finally, and that is not the topic here, is the hadronization of the heavy quarks, what we heard just, and the hadronic rescattering of the heavy mesons or baryons in the medium. In addition to all that, there is a question how to describe formally the passage of a heavy quark through the plasma. And there are also two groups or two different approaches. The one is based on the Fokker-Planck equation and the other on the Boltzmann equation. And to this I will come at the end of my talk. Now, first of all, the good news, most of the models which are in this comparison describe the heavy quarks RAA in V2 in a quite reasonable way. Here is not the last plot, but that one where I had most of the curves of the theory on it. And we see here on the left-hand side the V2 and the right-hand side of the RAA. And the error bars are still large, but in wide part, the quark models, the heavy quark models describe the trend of the experimental data and even quantitatively some of them quite nicely. So after this comparison that it works quite nicely is the question what we can really conclude out of this. What tells us this agreement and what can we take home or goes to the books which we would like to publish. And in order to answer these questions spontaneously, a couple of years ago now, a working group has been formed to make, first of all, the models comparable. Then second, to study how the different model ingredients influence the final result by replacing the specific ingredient of one model by a common standard. For example, for the expansion of the QGP. for the elementary interaction between the plasma partons and the heavy quarks, and for the initial condition. And this comparison has been possible due to many meetings at different places. I just mentioned here Berkeley, Leiden, Darmstadt, and Duke. And by this, we just advanced in order to make comparison feasible. Now, the participants in these comparisons, it's a little bit by accident, or people who have been interested, consisted of 6 groups, which were from Europe and the US, China. I just mentioned here the people who did the most work in blue. From Catania, it was Santos Das. Duke, it was Yingwu Xu. From Frankfurt, PhD, Teso Song. The same BNL, that was Chan Chan. And from North, we do not have a PhD student, that's Paul Bernardo Sio and Marlene Nagan. And from Tamu Sen Minhe, which we just listened to him a couple of minutes ago. Now, if one looks for the different programs, one sees already at the first view that the ingredients are not exactly the same. And then if you look in the details, there are really differences. So the difference is in the initial condition. The difference is also in the initial QGP condition. It is the transport theory for the quark-gluon plasma, where we have Boltzmann or hydro calculations here, or the EPOS hydro. Then the question is how the partons which are constituting the quark-gluon plasma are described, either as massful partons or as massless partons or as masses which depend on the temperature. We have different formation times of the quark-gluon plasma, which range between 0.3 Fermi and 0.6 Fermi. And the question is also addressed differently. What's happened when the heavy quark is created? What happens relatively fast because we have a hard process and the plasma is not yet formed. So there are either some collisions or there are no collisions. So these all kind of details were different in the different approaches. And for this reason, it was worthwhile to compare them. Now, the first question is how to compare the different approaches. A Boltzmann equation can be, under certain conditions, converted into a Fokker-Planck equation, and therefore the 2 different approaches, the Boltzmann and the Fokker-Planck equation, can be compared as soon as one has converted the Boltzmann equation into a Fokker-Planck equation. The Fokker-Planck equation in itself can be treated as a Langevin equation, and then we see that we have in principle the time evolution of the heavy quark, the position and the momenta, which are just given here by the velocity, and for the momenta just by 2 transport coefficients, that's a drift coefficient, and then we have here a random force, which has a mean value 0 if we have Gaussian noise or white noise, and which has a correlation which gives us basically 2 transport coefficients, the transverse and the longitudinal diffusion coefficients. So if we have converted a Boltzmann equation, then we are confronted with a transport theory which has 3 different coefficients, and these coefficients can be calculated in the framework of a Boltzmann equation. So for this reason, we decided to go to the level of a Fokker-Planck equation or Langevin equation to calculate for those approaches which have a Boltzmann equation, the transport coefficients, and then to start out from these transport coefficients. But the first thing what we observed is that the drag coefficients in the different model or the drift coefficients are rather different. Also, it is true for the diffusion coefficients, but I show here just the drift coefficient. We have here the 6 different models which are here. And if you look in details, and you see that it's basically the or the projection with the different colors. So all drag coefficients decrease with P, with the momentum of the heavy quark, and increase with the temperature, but the absolute values are rather different. So I may ask the question how this can come from, because all of them use in principle PQCD cross-section. But then if one looks into the detail of a PQCD cross-section, then one sees that the PQCD cross-section is not absolutely well defined. I mean, if we just take a T channel exchange, so it's a basic cross-section you can imagine, then we have 3 parameters which can be treated in the different models rather different. Also the Feynman diagram itself, and so the matrix element itself is basically calculated in the same way. Now this is, first of all, the coupling constant, which in some models is constant, in some models is temperature dependent, in some models depends on the transverse momentum squared. Then we have the masses of the incoming and the outgoing partons. They are sometimes with a mass in order to obey the equation of state we have from the lattice, and sometimes they are without any mass. We can also choose set the mass of the gluons, which is in the exchange. So it's a gluon exchange between the incoming particle and the plasma particle. That can be either calculated with what we did here, with the Debye mass multiplied by a factor 0.2. So I do not want to come to the details why we did this like this, but it's confronted with the gluon mass of the PHC model. And for this reason, we have now 3 different ingredients, which give basically 3 different, which we can combine now in all ways in order to calculate this A, this diffusion coefficient. Now, one sees in very high temperatures, several times Tc, they are not so far from each other. There is a factor of 2, basically from the masses of the heavy quarks against the 0 masses. But if it comes close to Tc, the coefficient is rather different. I mean, we have 2 orders of magnitudes here. And if you look really in detail, the largest drift you get basically if you have alpha, which is parameterized with the temperature and the mass 0 of the quark, whereas in the opposite, if the alpha is parameterized as a momentum transfer squared and with a different mass than 0 for the quarks from the plasma, then we get the lowest one. So even if we have the same Feynman diagram, the different ingredients which we have here, which we have to determine in order to make really a calculation, can vary substantially close to Tc, the different drift coefficients. Now, where can we get help from? One possibility is to go to the lattice calculation and to ask whether we cannot find something we can adjust to the calculation on the lattice. And what has been already discussed by Peter today, basically that's the spatial diffusion coefficient, which has been calculated for p equals 0 on the lattice with the formula which has been explained already today. They have some caveats which are not so serious for this discussion here, but at least one can calculate it for p equals 0. And then we can compare now with the calculations in the transport approaches, which are just taken here from these 2 publications. And we can calculate the same spatial diffusion coefficient basically in the limit of the momentum goes to 0 from the temperature times the mass times the drift coefficient, where this here is defined. Now, if we just plot it as a function of the temperature, here we are on the hydronic side, and therefore this spatial diffusion coefficient had been calculated by the hydronic degrees of freedom by Laura Trollos. Here we come basically to the quark side, and if we apply now one of these models, the PHSD model, then we find a quite nice agreement with this. But however, it does not help too much because we are always in the limit p goes to 0, whereas in all the calculations we need finally a finite p. Now, in order to get a little bit more forward in the comparison, we just took the models as they are, and then is given here on the left-hand side here for the drift coefficient and for the Q hat, which is the transverse momentum squared per unit length. Here, basically for the standard way, and here is here the first tune what we do. So that we need or we impose that's the best agreement in the RAA for that collision in the energy in the momentum range of the big quark between 2 and 50 GeV. Now, if we take this tune for all of the models, we see it doesn't help very much. The parameters which are here on the values of the drift coefficient or Q hat does not change very much, so it nails not down the situation which we would like to have. Now, this is here displayed as a function of the temperature for 300 MeV for the different momenta of the incoming quark. Here is for 30 GeV incoming momentum as a function of the temperature. But if you look at both of them, it's a huge variation of the coefficient, so this doesn't help too much. For this reason, we went to a second step. We had now a brick wall, and the heavy quarks enter this brick, and we compare now the results after entering this wall. Now, these are the results which we get without any tuning. So we see again a factor of 2 or even more of the differences in RAE. that is for T equal 2 Fermi over C, for 4 Fermi over C. And now we said, okay, we fix all these calculations by a common K factor, that at T equals 3 Fermi over C, we agree as best as we can. Especially, we have to agree at 15 GeV momentum of the heavy quark. If we do this, then we can look at, and with the differences now at 1 Fermi over C are not so large. So in principle, this fixes for the time when we do this calculation. Now, the RA is fixed by this condition, but of course, the other parameters are just given with a constant K factor in order to fix this. And if we go now back and look at the drift coefficient, we find that the variation is still quite considerable. Now, there is one difference is that we have now compared simulations which have elastic and radiative collision and only elastic one. So the drift coefficient is expected if we take just the elastic one different for both of them. But if we take the total one, it's still something like a factor of 2. And if you look for Q hat, where it's only the elastic collision, it's even larger. And that means if we now go and calculate in this brick wall, the average energy as a function of time of the heavy quark, the KT squared, or the KT squared microlongitudinal minus KT squared, then we find for 5 GeV here and for the initial energy of 30 GeV, so two different limits, that at 5 GeV it's relatively nice agreement, but if you go to higher energies, the agreements are not so nice anymore. And so for the energy is still relatively okay because we have fixed now the RAE, but if we look now for the transverse momentum transfer here, then it's quite a difference. So what can we conclude from this brick wall comparison? So also all models are internally consistent that we have checked, but I do not like to present it here. The different descriptions of the interaction between the heavy quarks and the plasma particles, so coded now as drift and diffusion coefficients, lead quite different results for the transport coefficients. They vary up to a factor of 2. Variation is temperature and momentum dependence, leads to a different energy loss and decoding even in a brick. That means the situation is much better under control than heavy ion reaction. Now, the difference cannot be resolved by a common K factor, as I have shown. We have fixed the K factor. Now, the origin of the drift and diffusion coefficient is not completely evident. Some of the origin we could identify, that are the finite parton masses to reproduce in lattice equation of state, and the radiation in addition to the elastic collision. So if we want to better understand the interaction, we have to do something else. We have either to ask our lattice colleagues to give us better transport coefficients in the kinematical regime we would like to have. Very complicated. We need new and better experimental data that will come in a couple of years, or we have that would be possible already today, model high multiplicity small systems where the situation is different as compared to the heavy ion collision. Now, in order to make progress, and because we have, as I said already, took models which describe the heavy ion data quite nicely, we made now the choice that we make the whole string of the interactions and what's happening from the creation of the heavy quark up to the final results of the detector modular, that we had for different initial conditions. We have different models which basically describe the heavy ion collision, the interaction between the heavy quark and the plasma particles. We have different mediums, hydrodynamic in 2 or 3 dimensions, or the transport approach PSSC, and then we compare the results depending which choice we have made for these different ingredients. And we took as well the Langevin equation in order to come to compare the results. Now the difference initial condition, or the influence of the initial condition to the final result. So we have the 2 different initial conditions, the PHST versus the Trento initial collision. Initial conditions are shown here in the coordinate space, and for the plasma and for the heavy quark positions. And when we run it, then we see that we have basically the spatial diffusion coefficient here going down. the momentum diffusion coefficient going up, so quite nicely, very similar. But if you look finally for the V2 of the sharp quarks, and especially for the V2 of the sharp quarks at mid-rapidity, then we see the differences are relatively large. I mean, we are talking about 15%. So 15%, we can just have different results if we have different initial conditions. Now, if we come to the time evolution of the plasma, what's happening there? Sorry, it goes always down. Then we see for now PHSD and Duke hydro 2-dimension, the same initial was 3-dimension, and now for the PhD time evolutions means the transport theory. Then we find that the RAA as a function of the rapidity is rather insensitive, so that is nicely reproduced. But if you come then, it's all before hadronization, to the RAA and so the V2, this one all at mid-rapidity, then we see that we get quite different time evolutions and quite different PT values or spectra at the end of the collision before hadronization. And that means the RAA here differs basically by 30%. So that here is the influence between the different transport theories where we have the same. So that's Duke hydro 2-dimension, Duke hydro 3 and PHSD. And between the red and the green, one sees the difference in the initial condition, what we have. So also here, by just this, we get basically 30% differences. So this ingredient also leads to this contribution. Now, if we look for the influence of the interaction of the heavy quarks with the quark-gluon plasma, we have here now the same QCD evolution, the different transport coefficients. So the only difference between these are now the transport coefficient. And we start out here again with the rapidity, which in the mid-rapidity region, the RAA is rather similar as before. Now, if we look now for the V2 or the RAA as a function of PT, we see for the small PT still agreement, but for the large PT, a huge difference. And that can be continued here, and that can be continued here. So for the V2 at mid-rapidity, and we see that also these different ingredients, if otherwise the whole reaction is described in the same model, we can get differences which are considerable. I mean, here we are basically talking about a factor of 3, and here basically about 30–40%. So this means that all these different ingredients, the initial condition, the interaction of the heavy quark with the quark-gluon plasma, and the expansion of the quark-gluon plasma in themselves is also something which can yield differences of the order of 20–30%. Now, for time-wise, I will skip this here because otherwise I do not come to the end. So let me come to the conclusion. The analyzing the models for the evolution of the heavy quark distribution, which all agree quite nicely with experiment, we see that there are differences coming from the different ingredients in the model. So each of these ingredients have 20–30% differences, and they compensate each other if one puts them all in a certain way together. So for this reason, even if we agree with experimental results, the different parts of the models can give a rather different value for the observables we are looked at. And for this reason, we have to get all these different parts of the evolution of a heavy quark in a quark-gluon plasma under control. We have already identified some of the reasons for this. This is the mass of the partons, and that is the inclusion of radiative energy loss. Others are still not identified and are hidden in these transport coefficients, which we compared in this situation. Now, we know in addition that the quark-gluon plasma is not completely equilibrated. We have high PT particles, which are not described by hydrodynamical calculations, and there the transport coefficients may be modified, as also has been shown in the framework of this comparison. Now, the perspective is that we need more tools in order to understand what's actually going on. We have, first of all, to improve the description in the transport theory. We have to identify when Boltzmann equations and Montgeval equations are necessary. And before the next round of data come, and we can hope that more data are available that we can compare to, we should check more in detail the prediction of the QGP expansion scenario to optimize our approaches. Then we should check more in detail the Hydronic rescattering, which is not negligible and which I have not included here in my report. And we should also check more in detail the hydronization process, because this is another source of uncertainty, as Min has already shown. If we look for the hydronization mechanism and set the RAA before and that is after hydronization, that is now from the EMI workshop where Min has reported, we see that the form of the RAA has changed quite a bit in the different models, especially at relatively low PT. And so therefore, in order to understand now the heavy quarks passing through the QGP and landing finally at the detector, this is another part which we have to get under control. And so a lot of remains to be done. Thank you very much.
Thank you very much, Jörg, for this report that nicely complements what Min showed us before. So I already see the hand of Peter Petretsky up.
Yeah, so I have a question. When you kind of calibrate your model and you compare with the lattice results. So the lattice results are, of course, in pure glue, and they assume the model calculation are done for 3 lights. So how do you do this comparison? And also related to that, when you show the decoupling result at leading order TNE more, I mean, is it kind of the strict leading order result, or is
yes,
some
I mean, that is
modification
the
of it?
basic. Yes, it's Swiatek and TNE more. That's all basically the same calculation. A fixed coupling constant, which is 0.3, and basically with fixed parameters, PQCD calculation. Now,
Yeah, but
can
shouldn't be negative? I mean, if you can look at the couple, you just insert the biomass, whatever decoupling you get, then
you insert an infrared cutoff, you take massless particles, you take alpha S equal 0.3, and so you have basically no temperature dependence of this process, and then you just calculated it. I mean, this is a relatively simple calculation. Now, when you come to the calculations here, that's a calculation done with PHSD model where gluons and quarks are present, and so one just calculated by means of this one, what I showed you here, the spatial diffusion coefficient. So it's of course not directly comparable with the calculation on the lattice, because the conditions here are different. I mean, that is just, you have here the interactions which are in this model, and so it's not a quenched approximation which is in the lattice.
So you shift, you assume that it scales with TC?
Here is, I mean, it's just a calculation. When we come here, I mean, the TC in this model, what I just advocated, PHSC, is given that it's in the transport approach, and then from this TC on, we go to lower temperature, and there we edit, or the model edit, basically the hydronic part, which has been calculated by Tolos, and that was surprising for us. It matches really nicely. There's no reason that it has to match besides physics, and so it seems to be a relatively decent description when one combines the lattice with the hydronic part.
Okay.
Do we have other questions? Yeah, Elena, please.
I just might be add to what Jörg said. Actually, it's not a PHSD calculation, it's dynamical quasi-particle model calculation, which is fitted to lattice data. I mean, properties of quasi-particles are fitted to the lattice data. And so it's not a PHSD in a box, it's just dynamical quasi-particle model. And here the critical temperature is just taken like in a lattice calculation for mu q equals 0. That's just comments. Thank you.
But that also explains why it is matching the lattice points, right? This is not an accident.
No.
To some extent.
No. Let me put like that. Sorry, it's misunderstanding. So I mean the properties of quasi-particle for light sector are fitted to the lattice results, to the equation of state and so on. And that is then you already perform the calculations with the charm particles. That's what comes out in some.
Okay, now it's clear.
May I emphasize? I mean, that is always a heavy quark which plays a role here, which is not determined by lattice calculation. So it's really the interaction which plays a role in the hadronic sector or in the plasma sector.
Okay, so I think time tells us we should move on. Thank you very much again, Jörg. And then we come to Steffen Bass, who will tell us about bulk evolution models of heavy flavor. So you should be able to share your screen.
Yes, let me do that and go into full screen mode. Can you guys see that?
Yes, looks good.
Yes.
Okay, well, this presentation is going to be more about the medium that our various calculations send the heavy quarks through. At least that's how I understood the task for this talk to be. And let me start out with a slide that I stole from Carsten Greiner many years ago, where he sort of showed the different ways that heavy quarks can interact with the QCD medium, and a large set of groups that have been working in this field. And so I think the point I want to make here is not to discuss all these different approaches. The point I want to make is that each of these implicitly relies on some description of the bulk medium, of the soft matter that provides the interaction partners for the heavy quarks. So the bulk medium is really, really important for what we do. And as we have heard in the previous talks this morning, there are significant discrepancies or uncertainties at the very least associated with that bulk evolution. All right, another thing I wanted to point out before I go into medias res is that there are, I think, two different energy scales that are probably sensitive to different things. Yes, if you go into the tomographic regime at sufficiently high energies, your heavy quarks will behave pretty much like light quarks. And a lot of effects become, better controlled or negligible. Yes, and it is really the initial medium composition and properties that is of primary importance. On the other hand, if you look at low and intermediate transverse momenta, and I think that a lot what's being talked about in this workshop focuses on this area, it is really the medium evolution and hadronization that play very, very important roles. Yes, and as was pointed out earlier, heavy quark collective flow per se does not prove thermalization. I think we now understand that the heavy quarks are sort of lagging behind in the properties of the medium, trying to catch up, but only if you make a calculation at very, very strong coupling, do they actually manage to catch up. All right, now there are different ways you can describe a soft medium for your heavy quarks to go through. You can use microscopic model, with a Boltzmann equation. You can use a fluid dynamical model. You can directly, set up a Langevin model where the heavy quarks are basically the particles that you propagate through some medium that again has to be provided by, a different calculation like a hydro. You can try to do hybrids where you combine macroscopic and microscopic degrees of freedom. And the choice of transport approach will allow you to study, different ways how the heavy quarks interact with the medium. Yes, I don't think we can go as far as saying there is going to be just one canonical medium, because different mediums will allow us to study different physics questions. Yes, but there are certain ways how to better control what kind of medium we use and thus minimize the uncertainties that Min and Jörg have talked about. So I want to spend the bulk of my talk talking about hydro, because I think that there are now some really good tools available that allow us to reduce uncertainties in that domain. And the way most of the hydro calculations in the soft sector, but also for heavy quark evolution work, is that you have some kind of initial state for quark-gluon plasma formation. And often for hydro calculation doesn't care where this initial state comes from, right? So you don't need a priori a first principles calculation like an IP plasma or so to start your hydro. You can use something simpler, which makes your life easier. Then you have a hydro evolution. You hadronize in the hydro. That makes your life a lot easier, since basically this is then driven by the equation of state that you can get from lattice. And then you can attach an afterburner for hadronic final state interactions. And I will show you two different afterburners and some good news about them. All right, so the initial state model I'm going to talk about a little bit more is a parametric model called Trento, which is readily available and simple to use. And it can be constrained by Bayesian analysis to provide actually a very good description of experimental data if you run it as a precursor to hydro plus afterburner. Yes, for heavy quarks, this slide may be somewhat out of date. There are a variety of ways how you can initialize those. What will be important is to make sure you are sort of consistent in the space momentum correlations that the soft matter initial state gives you. Okay, so this is just one slide to sort of flash out what Trento is all about. And at the basis, you have the nuclear thickness functions, TA and TB. And you basically map entropy density deposition or energy density deposition at the time of formation of the quark-gluon plasma to a function, a reduced thickness function that is a function of TA and TB. And there are some bells and whistles to take into account fluctuations. There are extensions of Trento that take partonic degrees of freedom into account. There's a whole body of work that I could spend hours on. But for the sake of what I want to talk about, let's just use basic Trento. Okay, here's what I meant is that you need to make sure that in your initial conditions you correlate your heavy quarks properly to the bulk, right? So you should use the same nucleon configurations that you have for TA and TB for the energy deposition in Trento, as well as for the determination of the production vertices for your heavy quarks. Yes, and you can see in the figure, a few examples of how that pans out. And yes, it's Monte Carlo, so it's probabilistic. And you can see on the far right for a peripheral collision that the one heavy quark production vertex actually does not sit in that hotspot, but that is just choice of one particular event. And if I would average over multiple events, then my heavy quark production vertices would correlate nicely with that hotspot that you see. Yes, but I think this is important to get your medium in sync with the initial configuration of the heavy quarks with which you do the calculation. Yes, okay. Fluid dynamics, I think I don't need to talk a lot about here. What I think we nowadays need to use is viscous fluid dynamics. Yes, since the choice of transport coefficients affects the way the bulk elliptic flow is being modeled. And the flow of the system will, of course, affect the flow of the heavy quarks, right? So I think ideal hydro is not ideal for what we want to do. Yes. All right. So here's part of the good news, namely that good viscous hydrocodes are nowadays readily available and they're open source, right? So nobody has to sit down and program their medium evolution from scratch just to do work in heavy quark theory or heavy quark evolution. Yes, for 2+1D hydro, there is the Vishnu code. Yes, for 3+1D hydro, there is music, and there's also the VHLLE code. And all of these codes interface to some Hydronic Afterburner. Yes. So that's I think that's really part of the good news. I would point out that I think Vishnu is written in Fortran. Music is written in C++. Yes. Now in all cases, what you have to do, of course, and I'll mention that a little bit later again, is that you have to, of course, calibrate the parameters of your hydro, for example, the transport coefficients or the initial condition parameters, to experimental data. But also there is a significant body of work and calibrations out there that you do not have to reinvent the wheel. Okay, when it comes to Hydronic Afterburners, there are two readily available. One is trusty old URQMD, developed more than 20 years ago. That model has had a surprising stamina, I would say, but it's written in Fortran, and it may not be the easiest to handle these days, where a lot of the programming environments that our grad students are used to are actually centered on C++ codes and Python. Yes, so there is a new kid on the block, Smash, which is a modern modular Boltzmann solver, and it has not yet reached feature parity with EuroQMD, but it will get there. I would say future support and development potential for Smash is a lot better than for EuroQMD. And so it may be worthwhile in terms of Hydronic Afterburners to at some point make the transition from EuroQMD to Smash. And there is already one well-established package out there, Jetscape, that has made this transition. Okay, and you may now wonder, how do we make sure that with a new Hydronic Afterburner, we don't sort of mess up all the calculations that we have done? For that purpose, a fairly detailed comparison was done between EuroQMD and Smash, and what you can see here is that these two models actually, for standard stuff, agree very, very well. Yes, so that that certainly increases our confidence that the Hydronic Afterburner side is well under control, and you don't have to worry too much whether you use Smash or EuroQMD. You're going to get the same kind of physics out of them. Okay, now of course, in order to make sure that your medium has something to do with what you measure, you have to calibrate your medium evolution to data, and then that is totally independent on what kind of model you use. Yes, for hydros, it's almost self-explanatory that you need to calibrate the initial conditions and the transport coefficients to describe the data. But even if you choose a microscopic model, there are parameters, either physical parameters or technical nuisance parameters that you need to tune to make sure that you describe the data. And this has become more and more difficult since there is a lot of high quality data out there, and I certainly believe that it is not sufficient just to calibrate on a few particle multiplicities or a few spectra, right? You want to use multiplicities, you want to use mean PTs or spectra, you want to use V2s, V3s, pretty much all the data you can get your hands on. And over the last decade, we have developed tools based on Bayesian statistics that actually allow us to sort of take the entirety of experimental data and calibrate all model parameters simultaneously at once. And for hydros, this has been now done multiple times. Here you can see one example of, I think that was the Vishnu hydro, 2D viscous hydro calibrated to a set of LHC data, lead on lead, and at 2 energies. And the agreement of the calibrated hydro calculation with those data is really, really good. Yes, and there are groups out there that are repeating this for a larger set of beam energies that are repeating this for different hydros like music. And so these calibrations are available. And thus, a high quality viscous fluid dynamic hydromedium is available for anybody who wishes to apply those to heavy quark physics. One thing I want to point out is a package called Jetscape. Yes, it is a software package based on a scalable modular architecture. It contains Trento for initial conditions. It contains music for fluid dynamics. It uses SMASH as an afterburner. It was originally devised to study transport and modification of jets. It also contains a set of tools for Bayesian analysis. But the point I want to make is that you don't need to do jet physics in order to use Jetscape, right? If you just want to have a well-calibrated hydro plus some initial condition model plus a Hydronic Afterburner, just take Jetscape and use it for that, right? Then nobody forces you to do anything with jets with the Jetscape package. And so you can utilize Jetscape very well without jet evolution models as a bulk evolution model and framework for adding whatever heavy quark evolution model you favor into it. Yes, and as one example, we have done that with LIDO, which is a linearized Boltzmann model developed in Duke by YRK. And that has been added to Jetscape as an external model in order to utilize the viscous fluid dynamical evolution. And so Jetscape can provide you with a well-calibrated bulk evolution pretty much out of the box. I mean, there is a learning curve, but it's not so bad, in particular, given that Jetscape runs annual schools that teach grad students how to use the package and make progress there. Now, something where I feel more work is needed, and that goes back to also the use of the Hydronic Afterburners, is hadronic rescattering for heavy quarks. Yes, there has been work in Texas A&M in terms of resonance scattering. Apart from that, the only other work I really know has seen attention in the community. So there's either the resonant rescattering, or there's the work by Ziwei Lin that's 20 years old. Yeah, so I wonder whether there is not a need to go back and look more closely into hadronic rescattering of heavy quark containing hadronic states. Yes, and that also goes to the point that these cross sections then would have to be embedded into our Hydronic Afterburners. Yeah, so in New York QMD, I think there is a version that does ZY Lin's cross sections. I'm not sure about SMASH, what has been embedded there, or whether they have embedded anything at all. But that is certainly something on the to-do list for the community, frankly, to pay some more attention to. Okay, here is just a slide to make the point that there is a lot of codes out there for bulk evolution that you can use and that are readily available and open source. Okay, technically your QMD is on a different license, but you can get your QMD and run it. That's not a problem. And you will get it as a source code, so you can take a look at it too. I should not totally ignore microscopic transport. Yes, microscopic transport has certain advantages, right? You have a consistent treatment of all degrees of freedom, medium and probes. You can do better treatment of non-equilibrium evolution. Fluctuations are in principle included. Yes. The problem I see with microscopic transport is, that you're often limited to a quasi-particle description. You're limited to cross-sections that are often calculated perturbatively, not always. PHSD does it differently. But there are some challenges in being consistent thermodynamically, where the hydro is, does it better, because it can directly use the equation of state, right? On the other hand, hydro has a local thermal equilibrium assumption, and it doesn't treat well of equilibrium in early time dynamics, and it has a lack of fluctuations in there. So, so depending on which question you want to address, you may have to switch to a microscopic transport evolution for bulk matter in order to have the proper medium for what you want to look at. And hold on, why? Yes, and you know, the two models I just want to highlight is in the old days, we had something called the Parton cascade model that was fully based on PQCD degrees of freedom. You know, a newer incarnation is bumps. Not sure whether anybody from bumps is actually here at this workshop, but it is certainly a capable model. And yes, I'm almost done, Johanna, no problem. And by the way, the Parton cascade model is not dead. These days, it's just not called Parton cascade model, but there are a lot of groups that are using what they just call kinetic theory to study early time dynamics. And if you look under the hood, then a lot of this is very, very similar to what we would call a Parton cascade model. Yes, and I should, of course, you know, I have to mention PHSD as one of the more impactful models that we have, in particular also in this workshop, for a microscopic evolution of bulk matter. Okay, and I am done. Thank you. I did not put a conclusion out there, you know, it's my whole talk was a conclusion.
Okay, thank you very much for these thoughts and bringing us up to date on these evolutions. I see already hands up, but I would like to use my privilege as chair of the session, since you mentioned in the end a lack of fluctuations in hydro. I would like to mention that there is one completely different hydro code out there, and that's the one by Stefan Flörchinger, Fluidum, which works with mode expansion, and that has fluctuations. That's one advantage, and the other is that it is very time efficient. It is many orders of magnitude faster than anything else out there.
Okay, thank you.
Okay, so then I think Jörg Eichelin was first.
Just one comment and one question. The comment is, I mean, there are these calculations from Laura Tolos and Juan Torres about the meson hadron scattering. And they show that it's really important to have this scattering in. So I do not see that it's really so easy to neglect these interactions completely. The second, that was my comment. The question is, I mean, you made a big point out of the similarity of SMASH and URQMD. But if I remember correctly, I mean, the cross-section at these energies, at least in SMASH, are those from URQMD, or I'm mistaken. So for this reason, I think the agreement is not that astonishing.
Can you repeat your question again? I was somewhat distracted.
The question is, URQMD and SMASH share, I think, the cross-sections, which are relevant for this energy regime. So for this reason, I would not consider it as a big wonder that they agree now. The question is whether these both agree with the others, but among themselves, they should agree.
So Jörg, yes and no, right? So the cross sections were re-implemented into SMASH, right? So it's not like somebody lifted the cross-section codes out of URQMD. Yes. So they were sort of reparameterized for the use in SMASH. Yes, and I think that is an important distinction. Yes, since quite often when we have discrepancies between codes that want to do the same thing, you have to make sure it is physics and not programming or simply a bug, right? And SMASH redid everything from scratch, and so I think this is an important confidence builder there in that respect. And and then in the same vein, JAM is a URQMD clone, so to speak. I did not mention it here, because nobody uses JAM as an afterburner, or very few people do that. But you know, there it was probably much more closer to taking exactly what was programmed in Eurocube. Yeah, so I think but yes, you know, hadronic interactions, we all know what we need to put in. Yes, the pi-pi cross section and the pi-nucleon cross section and all that. So if you do a decent job at putting in those cross sections, you should get the same out. I mean, the basic physics at hand is not a question.
But along the same vein, of course, these cross sections for heavy flavor hadrons are largely unknown.
Yes, correct.
And as you pointed out, this may need additional work.
Yes.
Okay, then Elena has her hand up.
Actually, Stefan, I just want a little bit elaborate what Jörg said concerning the importance of hadronic cross-section, and you are absolutely right. Indeed, they are important. For example, in PhDs, they are responsible for quite a fraction of V2. So formation and so on. But I just want again to say that of course, many of these cross sections are unknown experimentally. You have to build a model. But as Jörg mentioned, there is efforts in this direction, and that is precisely done by Barcelona Valencia group. For example, there is a effective chiral Lagrangian approach based on heavy quark spin symmetry developed by Cabrera and Juan Torres, Recon, and so on, other people. And then they describe d meson scattering with meson. And also on baryonic sector, there is a Laura Tola's group working, and they did a G matrix calculation when they coupled to nucleon octet and delta decuplet, actually. And I just want to say, and that's precisely in PhD, we implemented these channels. Taiso did it. It's more than 200 channels. And well, in this case, it's really rather important. I wouldn't say that it's fully complete. For example, there are interactions which is with the vector mesons which are missing in these coupled channel approaches. And in this direction, it would be very important to bring attention to our many body colleagues doing such type of chiral approaches, also to provide us with this input. But I just want to say that in principle, that's available, even parameterized, and could be taken and implemented. Okay.
Oh, so then the to-do list would be really for the groups who maintain those often used afterburner codes to actually work on these implementations. And that's not something I've seen yet.